Okay, let me connect the writing pad. So let us wait for 5 minutes for others to join, and then we'll proceed with today's session. Okay. Okay, so I think we should start with today's session. So this is the last session, problem solving session for the course of Introduction to Fluid Mechanics. So let me introduce myself. I am Kalpita Nath from IIT Kharagpur. I am research scholar at IIT Kharagpur, and this course has been instructed by Professor Suman Chakraborty, and this is the last problem solving session. So I hope you have undergone through all the problem solving sessions and also the videos that have been uploaded, and I think I was able to solve your doubts regarding all those sessions and the problems that are being solved over there. And okay, so let us proceed with today's session. Okay, first of all, we'll go through what sir have gone through in the class. So first of all, we'll start with Hagen-Poiseuille's equation, that is a fully developed flow in a circular pipe. So let's suppose there is a circular pipe. Okay, so this is a fully developed boundary layer over here. Okay, and this is the axis. So the radius, and like let's suppose up to this point the flow was just developing, so this was the boundary layer before that, right? And at this point flow become fully developed. So this is R and this is Z, and if this is a circular region cross sectional area and this is the midpoint, so this is theta, right? So like this is the radius R. Some other color. This is the radius R of the pipe, and this is the horizontal. So this is the angle theta with the horizontal. That means this is angle theta, right? So this is an inclined pipe. So this is angle theta. This is Z, right? If this is G, then how can we divide G into its corresponding components? This is G, this is theta, this is G cos theta, and this is G sin theta. So the body force in direction of R will be, this is R, right? This direction is R and this direction is Z. So in the direction of R it will be minus G cos theta obviously, and in direction of Z is minus G sin theta. Now for the developing region, velocity will be a function of R and Z both. But for the developed region, velocity will be a function of R. This we already know. Now, from the continuity equation, del rho del T plus del of rho V is equal to 0. Right? If we'll separate it, so if it will separate it, this will be del rho del T plus 1 upon R del R rho R V R plus 1 upon R del del theta rho v theta plus 1 of del del z rho vz is equal to 0. Now, we are taking axis symmetric. That means any quantity that will be differentiated with respect to theta will be 0. Right. Now, axis symmetry does not necessarily say that v theta will be 0. But any differentiation with respect to theta will be 0. Right. So, as the flow is fully developed, so this thing will be 0. That means the velocity won't be changing in z direction. Right. And as the flow is axisymmetric, so this thing is 0. So what is left? Left is this we are taking steady state, so density anyhow is constant, so this del rho del t is 0. So del del r of rvr is all left, that would be equal to 0. That means rvr is not a function of r, right? Now the boundary conditions, there are two boundary conditions. That means that r is equal to r, vr is equal to 0, and vr is equal to 0 for all r. That means vr is not a function of r. Except r is equal to 0, that means a singularity case. Now for this problem, uh, like if we consider there is no swirl, right? No swirl means v theta is 0, right? Now, if we write the momentum, theta momentum equation, then theta momentum equation is rho del v theta del t plus vr del v theta del r plus v theta by r del v theta by del theta plus vz del v theta by del z is equal to minus 1 upon r del p by del theta plus mu del del r of 1 upon r del del r of r v theta plus 1 upon r square del square v theta by del theta square plus del square v theta by del z square plus 2 upon r square del v r by del theta plus rho v theta. Let me use some other color. Now we'll cancel things out. Obviously, steady state, so this is 0. uh, v theta itself is like v theta itself is 0 with respect to theta, because axisymmetric this is 0, and because fully developed this is 0, right? And because axisymmetric this is 0, v theta itself is 0, and axisymmetric, so this is 0, fully developed, so this is 0, again axisymmetric, so this is 0. Now v theta is equal to 0, del del theta for any component is 0, and del vz by del z is equal to 0. Yeah, so all this is 0. Now if we will write the r momentum equation, right? So for r momentum equation, again we should write all the things, all the terms. So del vr del t plus vr del vr del r plus v theta del vr del theta minus v theta square by r plus vz del vr del z is equal to minus del p del r plus mu del r 1 by r del r of r vr plus 1 by r square del square v r del theta square plus del square v r del z square minus 2 by r square del v theta del theta. So let me use some other color. Now steady state, so this is 0, vr is 0, uh, vr is 0, so and v theta is 0, again with respect to z because of fully developed 0. Now this is not 0, this is not this is 0, right? And another thing is this is also 0, this is 0, this is 0. So what is left? What is left? Plus rho br is there, so this is left. So if we will write things up, so this will be 0 is equal to minus del p del r plus rho br. Now rho br we have already determined here, right? Over here rho br, br means g cos theta minus g cos theta. So rho br will be minus g, like only br will be minus g cos theta. So this will be del p del r is equal to rho g cos theta, right? Now we will write what? Lastly, the z momentum equation. If we will write that, this will be rho del vz del t plus vr del vz by del r plus v theta del vz by del theta plus vz del vz by del z minus del p del z, along with that minus mu 1 upon r del r of r del vz del r plus 1 upon r square del square vz by del theta square, this one, plus del square vz by del z square plus rho bz. So let us cancel things. So again this will be 0, this will be 0. Actually here why it is 0? Cause vr is 0. That's why this is 0. So cause del vz is sorry, vz is not 0, right? So del vz del r is not 0, but vr is 0, so that's why this is 0. V theta is 0 and del vz del z, this is also 0. Now in all of this, this is 0, axisymmetric, this is 0, fully developed, right? So many things are left now. So what are those? Del p del z is equal to mu 1 upon r del r of r del vz by del r minus rho g sine theta. So we can take these two together, right? So from the r momentum equation, we got to we got this equation, right? So this equation if we'll write up from r momentum equation, so that means minus del p del r minus rho g cos theta. So if radius of the pipe is not that large, then we can take this to be 0, right? So if this is 0, dp dr is equal to 0, that means p is not a function of r. That means p is a function of z only, because the flow is axisymmetric, so p cannot be function of theta, right? So now from the z momentum equation, from this equation, if we will write this, so we can change the partial differential equation to we can remove the partial differential equation and we can give normal derivative. So dp dz, cause it is a function of single thing only, sine theta is equal to mu and also vz is function of r only, it's already defined earlier. So d dr of r dvz dr. Now this we can write as P star, right? Where P star is equal to P plus rho gz sine theta. So this is H. So this is piezometric head, right? We already know about this. So we can write this as dp dz is equal to mu 1 upon r d dr r dvz dr. Now this is a function of r only, and this is a function of z only, right? So we can take both of them equal to constant. So on the right hand side, if you take as constant, so d dr of r dvz dr is equal to c by mu r. Now r dvz dr is equal to c by mu r square by 2 plus c1. So dvz dr is equal to cr by 2 mu plus c1 by r. Now integrating again, vzr is equal to cr square by 4 mu plus c1 ln r plus c2. So this is equal to 0 by boundary condition 2, right? Boundary condition 2 means r is equal to 0, v is finite, so this will become 0, symmetrical boundary condition. And for r is equal to capital R, vz is equal to 0, that is boundary condition 1. If we'll put, so this will be 0 cr square by 4 mu plus c2. Now c2 will be what? Minus cr square by 4. Therefore vz, if we'll write, that will be is equal to cr square by 4 mu minus cr square by 4 mu. That means minus cr square by 4 mu 1 minus small r by capital R, small r square by capital R square. So this thing can be written as dp star dz, and has to be negative to drive the flow in the z direction. That's why this the negative thing comes, right? Now from here we can write the average velocity. This can be written as this. So this is 0 to r 2 pi r vz dr, right? And this is pi r square. So this will come out to be 2 upon r square, 0 to r vz r dr, right? Now we can write c in terms of v bar, right? If v bar we write in terms of like in terms of c also, like vz we need to put over here na and integrate it. So if you're integrating it, like I won't do much I won't go to much details of integration, you can do it on your own. So this cr square, this will come out to be cr square upon 8 mu. So if this comes, then c we can write as minus 8 mu v bar upon r square. So this can be replaced in Vz. Vz is equal to 2 V bar 1 minus small r square upon capital R square. So this is parabolic velocity profile. Now wall shear stress TWRZ is equal to minus mu del Vz del R minus mu del Vz del R plus del Vr del Z. Right? This we already know, smaller is equal to capital R. So this is 0 because of the axis because of the boundary developed boundary layer, fully developed boundary. So this will be 0. Now this negative sign is because the r direction points towards the wall from the center line, that's why this negative sign. So tau w small r is equal to capital R is equal to 4 mu v bar by capital R. Now the coefficient of friction is, if we'll find out, this will be tau w 1 by 2 rho v bar square is equal to 16 upon Reynolds. This we'll find out, this fanning friction coefficient. Now dp star dz, if we will find out dp star dz, so what we want to do, we want to find the friction loss. If we want to find friction loss, what we will do, dp star dz is equal to minus 8 mu v bar by r square. Now this is p out minus p in upon L, right? So this will be minus 8 mu v bar upon r square. That's true, right? So this will v bar will be this we can write as, one second. So this we can write as hf rho g, the head in terms of head, upon L is equal to the loss 8 mu v bar by r square is equal to 32 mu v bar by t square. Now v bar is equal to q upon pi d square by 4. So this we can write as rho GHF is equal to 32 mu QL upon, like we can write in this equation. This we can write in this equation. So pi d square by 4 d square. So HF, if we'll find out from here, this will be 128 mu QL by rho G pi d3 power 4. This is the famous equation that is well known, so well known. So this is the Hagen-Poiseuille's equation. So if we'll write the head loss expressed in terms of fraction of kinetic head, so we can get Darcy's friction factor. Darcy's friction factor can be represented as, Darcy's friction factor is 64 upon Reynolds number. Now the power required to overcome the head loss, like that also can be found out. So the formula for that is rho GHFQ. So delta P star, because this delta the pressure head into flow rate, the pressure loss into flow rate. So that's it. The pressure loss is rho GHF, right? So we can use that later on. So okay, let's see. Let's like if I give you a question, like let's suppose there is a pipe that has plated into two parallel pipes. Let's suppose Q is the flow rate here, and this is L1 D1 F1 Q1, this is L2 D2 F2 Q2. Now L1 is equal to L2, F1 is equal to F2, D1 is equal to 3 centimeter, D2 is equal to 6 centimeter. Now HF1 is equal to 0.64. So what is HF2? Obviously, since the head loss remains same in parallel connection, head loss remains same, like in this half and this half, head loss will be same. So HF2 will also be 0.64. Is it not? Any doubt? So let's proceed now. Now for the next question, this is only the question where D, like the structure will be same, but here D1 is equal to 4D2 and F1 is equal to F2, L1 is equal to L2. Now for parallel connection, like we need to find out the ratio of Q1 and Q2. So that is the main question. So okay, let's give you 2 minutes for this. I'll wait for 2 minutes and then we'll proceed with the solution. Should we proceed with the solution? I think we should, because there are lots of problems that we need to solve today. So, if you want to go for its solution, we already know that the total flow rate is equal to Q1 on the arm 1 and Q2, right? So, and the frictional head loss on 1 and 2 are similar. So, if you write this up, so this will be 16 FeLeQ square 2g pi square d to the power 5. So, this will be is equal to 16 F1 L1 Q1 square 2g pi square d1 to the power 5 is equal to 16 F2 L2 Q2 upon Q2 square upon 2g pi square d2 5. So let's take this some constant k. See. So this q1 square is equal to k. Let's suppose this is c. Use some other color. Let's suppose this is c. This is c. So q1 is equal to k d1 to the power 5 c f1 l1 and q2 square is equal to k d2 5 c f2 l2, right? And q equivalent is same. So q is equal to q1 plus q2 and here it will be equivalent, so d e to the power 5 upon f e l e is equal to root over d1 to the power 5 f1 l1 plus root over d2 to the power 5 f2 l2. Now hf1 is equal to hf2. hf1 is equal to hf2. So 16 f1 l1 q1 square upon 2g pi square d1 to the power 5 is equal to 16 f2 l2 q2 square by 2g pi square d2 to the power 5. So if we will cancel things out from here, so here f1 is equal to f2, so everything is like that. So we can write q1 square upon d1 to the power 5 is equal to q2 square d2 to the power 5. The others are equal, so it gets cancelled out. Like it gets cancelled out. So q1 q2 is equal to d1 upon d2 whole to the power 5 by 2. So d1 is 4 times of d2. It's already given in the question. So this is 5 by 2, this is 32. That means q1 by q2 is equal to 32. Yeah. Now the next question is, let's suppose there is another like expansion, sudden expansion. So this is dB and this is dA, like cross section, like diameter of A and diameter of B. This is again LA and this is again LB, right? For pipes A and B connected in series, dB is given as twice of dA and dLB is given as 8 times of LA. FA is equal to FB, frictions are same. So we need to find HFA upon HFB. So there is one let me give you the start of this problem, how to solve this. So for pipes that are connected in series, we already know that HF is equal to, that is the head loss, is equal to HF1 head loss due to friction plus HF2, right? So this means 16 F equivalent L equivalent Q square upon 2g d e to the power 5 pi square. So this equal to 16 f1 l1 q square upon 2g d1 to the power 5 pi square plus 16 f2 2 L2 Q square upon 2G d1 to the power 5 pi to the power d2 to the power 5 pi square. So others if will cancel, so this is FELE DE to the power 5 is equal to F1 L1 D1 to the power 5 plus F2 L2 D2 to the power 5. So this is very easy, right? You just solve this, like it will not take more than 10 seconds. Please solve this. Okay, so let's solve this then. So for about this, it will be like, just write it in simple form. HFA upon HFB is equal to FALA upon DA to the power 5 upon FBLB upon DB to the power 5. So this will be 32 by 8, that means is equal to 4. Let us solve one problem for dimensional analysis. So the okay, we'll solve it later. We have one problem for dimensional analysis, we'll solve it later. Now, see, for dimensional analysis, we know there are two types, prototype and model, right? And the similarity is in case of geometric, that means similarity of geometry, or it is kinematic, that is similarity of motion, or it is dynamic, that means similarity of forces. The physics of the problem should remain the same. So the checking of the non-dimensional parameters to the physics of the given problem. So we'll apply Buckingham theorem when there will be dimensional analysis problems will come into picture, right? So yeah. Now, let's proceed to today's problems. So this is the first problem for today, where the pump of water distribution system is powered by 15 kilowatt electrical motor whose efficiency is 90%. The water flow rate through the pump is 50 liter per second. So volumetric flow rate is given, efficiency is given, the diameter of the inlet and outlet of the pipes are same, and the elevation differences across the pump is negligible. If the pressure at the inlet and outlet of the pump are measured to be 100 kilopascal and 300 kilopascal, the pressures, absolute pressures are given, and the mechanical efficiency of the pump and the temperature rise of the water as it flows, we need to find out. Like temperature rise, like there will be some difference in uh, uh, pump, right? So there will be some difference in how should I tell you? Like, see, whatever the power is provided to the pump, all of the power is not transferred to by the pump to the fluid. So some of the losses that are calculated in losses, those are used in rising the temperature of the rising temperature of the fluid, right? So that is what we need to find out here. Okay, so before that, like, let me go into some detail of what other things I have covered this week is Darcy's equation. We already know that is F L by D U bar square by 2G. We already know this. So if a pipe is there in atomic scale, there is some irregulations in the pipe. So in laminar flow, those irregulations doesn't come into picture. But in turbulent flow, what is happening? Epsilon, epsilon, that is the height of these perturbations. Those are important because they the velocity is very high. So these perturbations will be affecting the fluid flow, right? So what is happening? The perturbations are not allowed to grow, and whatever disturbances are created by the wave, that get instantly damped, get damped out almost instantaneously. Thus the effect of wall disturbance is not important in case of laminar flow. But in case of laminar flow, the surface, like in case turbulent flow, the surface roughness is important, right? So in case of turbulent flow, what is happening? One diagram that is called Moody diagram or Moody chart, that is been used. Like, what is this Moody chart? There will be some friction factor there in this side, like this will be epsilon by D, that will be like moving on from this side to that side like this, right? And this is Reynolds number. So depending of either, like if F, we need to find out these things, we need to know, and we can calculate F like that. At very high Reynolds number, the friction factor tends to become independent of Reynolds number. This independence starts more quickly for mode of pipe. The viscous sublayer that is present in the turbulent layer, the lowest, that the layer that is very close to the surface is the viscous sublayer. That becomes thinner and thinner as one approaches to the high Reynolds number. Thus, the outer flow is exposed to the wall, and the wall roughness, and the viscous sublayer becomes thinner and thinner. Thus, the form drag is very important when the surface roughness protrudes into the outer layer and the viscous sublayer is very small. So at that time, it is very important. When the form drag and Reynolds number is very large, the friction factor is almost independent of Reynolds number. And as form drag is what it dominates, not the skin friction drag. Okay, so before we move to this question, so let me introduce the questions that sir have done in the, like, sir have taught in the class. If we'll go to a bit detail of that, then it will be easier for us to solve today's problems. So first question that is he has introduced is L is given as 300 meter, dia is given as 150 mm, the volumetric fluid is given as 0.05 meter cube per second. The kinematic viscosity is given as 1.14 10 to the power minus 5 meter square per second, and epsilon is given as 0.15. Surface roughness is given as 0.515 m. Epsilon by d. Oh, I forgot to tell you, epsilon by d. Why we consider epsilon by d? Because, like, epsilon is a term, like, it is surface roughness, but we need to consider it with respect to the pipe to maintain a constant, like, dimensionless value. So that's why we are using epsilon by d. Now what is the power, so we need to find what is the power required to drive the fluid, right? So power required to drive the fluid, so for power required, we know that power is equal to rho g q hf. We have already learned about it, and hf is f l by d u bar square by 2g, right? So q is already given, so v bar we can calculate from here, and if v bar we can calculate from here, Reynolds number we can calculate from here. So Reynolds number we know, epsilon by d we can calculate, so we can find what? Skin friction. So this we can put here, right? So let's give us 2 minutes for solving this. Like, I have already solved this problem, so I'll discuss this with you. First, you try on yourself how to solve this. Like, let's give 2 minutes. It's already 5. Like, our class will continue up to 6, so it's already 5:01. So let's give 2 minutes for solving this, and then we'll proceed with the solution. Okay, so let's solve this, or like let's discuss the solution actually. So first of all, we need to find the average velocity. So that will be q upon pi d square by 4. So that if you'll calculate, that will come out to be 2.82 meter per second. Density is known, and density and average velocity is known. So Reynolds number can be calculated. Reynolds number will be rho u bar d by mu. So that means u bar d by nu. So all of them are given. So this will come out to be 37105.26. You can calculate yourself back at home, and you can cross check with this. Now, if we will open the Moody's plot. Let me share the Moody's. Let's share this. Share this. Okay, that broadcast is 1 second. So I've prepared many questions for today. I don't know whether I'll be able to solve all of them, but let's try. Okay. So just let me show Moody's chart once, and later on you can open it by yourself only, and you can check. Okay. So this is the Moody's chart. So what are the values for us? So it is 3.7, like 3.7. That means almost 4 into 10 to the power 4, and 4 into 10 to the power 4 is the Reynolds number. And epsilon by d also we have calculated. Epsilon by d is 0.001. You can calculate by yourself as well. So epsilon by d is 0.001, 0.001, this one, right, this one. And Reynolds number is something in 10 to the power 4. So this one, and 10 to the power 4. 4 into 10 to the power 4. So almost here. So so this is 4 in 10 to the power 4. That means here almost. So here and 0.001, 0.001. It will almost come around, friction factor will almost come around 0.023 approx. Right. So this is what we got, and open this up, the writing pad. So now we need to find HF. So HF will be is equal to FL by D U bar square by 2G. So this means 0.002 into 300 upon 0.15 multiplied by 2.82 whole square by 2 into 9.81. So this will come out to be 16.213 almost. 23. So the power will come out approximately to be 8.165 kilowatt. So this is what sir have also got, right? So I got approximately to be 7.952 kilowatt, almost is equal to 8. So you can find out yourself what you have got for the value. Now for the next example also, for the next example, nu is given as kinetic viscosity is given at 10 to the power minus 5. This is example 2. Diameter is given as 100 mm. Epsilon is given as 0.25 mm. And HF is given as 5 meter of oil. L is given as 120 meters. So we need to find Q. So now we need to read from the Modi's diagram and find epsilon by D, but Reynolds number we don't know. So Reynolds number we need velocity for that. So we'll put a guess on friction factor. So let's suppose let us put a guess on friction factor, and whatever guess we feel will use, from that guess we will we already know epsilon bar by D. So and from that guess of friction factor, from the Moody's chart we can find Reynolds number. Corresponding to that Reynolds number we'll find one velocity. So from corresponding to that velocity we'll find one, like in the HF equation we'll find F. So that is a new F. That F like whenever like that F will be our new F, and from that F we'll recalculate everything again, and we will not stop the iteration unless and until this old F and new F are equal or approximately equal, right? So that will be the point of convergence. So for here I have started with 0.004 F value 0.004. So 0 point, like from Moody's chart we found that okay, so we found that epsilon by D we have calculated as 2.5 into 10 to the power minus 3, and from Moody's chart we found that Reynolds number is 4 into 10 to the power 3. So from that U bar we have calculated as 0.4, and from that HF is equal to 5 is equal to F into 120 by 0.1 multiplied by 0.4 square by 2 into 9.81. So from that F we got as 0.5109. So we have to recalculate it again, and in that way, cause it have diverged a bit, so we have to recalculate again. I think there must be some mistake, and the final F will get as 0.03, right? Now, similar way, we have another question, that is L is given as 180 meter, Q is given as 0.085 meter cube per second, and HF is given as 9 meter. Nu is given as 1.14 into 10 to the power minus 6. Okay, and epsilon is given as 0.15 millimeter, and diameter we don't know, we need to calculate that. Again, like we'll guess one f, and from that guess value we'll calculate the sorry, epsilon d is epsilon by d we do not know, right? So from that f, q is given. So from that q, we sorry, like Reynolds number also we don't know, epsilon by d also we don't know. So what we'll do, we'll guess some f. From that f we'll calculate hf, and from that hf we'll calculate diameter. From that diameter we'll recalculate that Reynolds number and epsilon by d, and after calculating all those, we will just put in the Modi's plot, and from we'll calculate f. So that f should be equal to the previous one. So over here what we did is, for the first case we have thought f to be 0.02, right? From that, what we did is, we calculated that, see, hf is given as 9 is equal to fl by gt 0.0058 upon d to the power 4. So from here f we have calculated, right? D to the power 5. So f we have we have, if we have guessed f as 0.02, so from here d can be calculated. So d have been calculated as 0.188 meter, right? If d have been calculated as such, the Reynolds number can also be calculated, du bar by nu. So it came out to be 5.05 into 10 to the power 5, and epsilon by d came out to be 8 into 10 to the power minus 4. So from the Modi's plot we got f nu. F nu is equal to 0.018. Now f nu, now this is the new f old. So 0.018 is the new f. Now d again we have calculated as 0.184. Reynolds number we have calculated as 5.15 into 10 to the power 6. Epsilon by d we have calculated as 8.15 into 10 to the power minus 4, and from the Modi's chart we have calculated f nu as 0.017. Now, so as this is almost equal to 0.01, so we have taken f to be 0.0175. So this is it. Let's now proceed to the question that we have started. So yeah. So first is question number 1 is this one, which you can see, which you can see in the screen. So it's written that the pump, like as I have already explained this to you, so I think you should take 2 minutes to solve this problem. Okay, then we'll proceed with the solution. So I think we should proceed with the solution. So what will happen first? The mass flow rate of water through the pipe is written as density into velocity. So sorry, volumetric flow rate. So that is 1 kg per liter into 50 liter per second. So that is 50 kg per second. Now the motor draws 15 kilowatt of power and it's 90% efficient. Thus, the mechanical shaft power that it delivers to the pump is eta motor into the power that it delivers, the electric power that is delivered to it. 0.90 multiplied by 15 kilowatt, that means 13.5 kilowatt. Now, to determine the mechanical efficiency of the pump, we need to know the increase in the mechanical energy of the fluid as it flows through the pump, which is delta E mechanical energy of the fluid. Change in mechanical energy of the fluid is the mechanical energy of the fluid at outlet minus mechanical energy of the fluid at inlet. Right. So this is equal to mass flow rate P2 upon rho plus V2 square upon 2 plus GZ2 minus m dot P1 upon rho plus V2 square, sorry, this is 1 upon 2 plus GZ1. So simplifying it for this case and substituting the values, if we'll do that, see, velocity is the diameter is same all the way, so the velocity will be same, and it is horizontal, z1 is z2 will also be same. So only thing that is left is p2 minus p1 upon rho. So this is 50 kg per second multiplied by 300 minus 100 kilopascal. So we'll change 1000 kg per meter cube, 1 kilojoule, 1 kilopascal meter. So this is equal to 100 kilowatt, sorry, 10 kilowatt. Now, the mechanical efficiency of the pump thus becomes what? Mechanical and efficiency of the pump. So that is the power of the pump minus power of the pump shaft. So that is equal to the change in mechanical energy of the fluid upon the power of the shaft, pump shaft. So this is 10 kilowatt upon 13.5 kilowatt. So that is 0.741. That means 74.1%. Now this is part A, like what is the efficiency. Part B, what they have asked, temperature rise. So of the 13.5 kilowatt of the mechanical power that is supplied by the pump, only 10 kilowatt is imparted to the fluid, as I've already explained you earlier, as mechanical energy. The remaining 3.5 is converted to thermal energy due to the frictional effects, and this is lost mechanical energy that is manifested as heating effect in the fluid. So this mechanical energy is equal to pump shaft weight of the, like say, the power delivered by the pump shaft minus the power delivered to the fluid. So this is equal to 13.5 minus 10. This is equal to 3.5 kilowatt. Now, temperature rise of the water due to the mechanical inefficiency is determined from the thermal energy balance. So this mechanical energy that is lost is equal to m dot u2 minus u1. So this is mc dot delta t. So therefore delta t is equal to E mechanical loss, the energy that is lost upon mc. So this is matlab mcp delta t, right? So this is 3.5 kilowatt upon 50 kg per second multiplied by 4.18 kilojoule per kg degree Celsius. So this is 0.017 degree Celsius. The water will experience a temperature rise of 0.017 degrees Celsius due to the mechanical inefficiency, which is very small, and as it flows through the pump. Okay, so I hope you have understood this. So let us proceed to the next question. Oil at 20 degrees Celsius, density and viscosity is given, is flowing steadily through a 5 centimeter diameter, 40-meter long pipe. The pressure at the inlet outlet is given as 745 and 97 kilopascal. So determine the flow rate of the oil through the pipe, assuming the pipe is horizontal and inclined 15-degree upwards and inclined 15-degree downwards. So before also verify the flow through the pipe is laminar. So before going like you solving this, first of all let us derive for the inclined pipe what will be the formulas. So this is a pipe, inclined pipe. This is, let's suppose, a small elementary area that we have taken as dr, right? And this thing, and this is dx, right? So this is theta, the horizontal, the angle with the horizontal. This is x and this is r. So if we'll take this will be w sine theta. This is the weight w. This is tau r. This is p x plus dx. This is tau r plus dr, and this is px. This is theta. Now the weight in x is w sine theta is equal to rho g v sine theta is equal to rho g 2 pi r dr dx sine theta. So if we'll do the force balance, that will be 2 pi r drp at x minus 2 pi r dr p at x plus dx plus 2 pi r dx tau at r minus 2 pi r dx tau r plus dr minus rho g 2 pi r dr dx sine theta is equal to 0. This, what it happens, mu upon r d dr r du dr is equal to dp dx plus rho g sine theta. Now the boundary condition are at r is equal to 0, du dr is equal to 0, at r is equal to capital R, u is equal to 0. These are two boundary conditions. Now solving, if we'll solve this, u r will get as minus r square by 4 mu dp dx plus rho g sine theta 1 minus small r. Okay. Sorry for the disturbance. Uh, so u r we were defining, so this is minus r square upon 4 mu dp dx plus rho g sine theta 1 minus small r square upon capital R square. Now the average velocity. I think you've understood, right? So this was the if this was the whole like pipe, so this elemental area we have considered, so this is dr and this is dx, so this is theta, this is x and this is, so force balance again, and let me write 2 pi r drp at x minus 2 pi r drp at x plus dx. Cause if this is the this will be here, it will be tau r plus del r dr, and here it will be tau r. Here it will be p at x, and here it will be px plus dx. Simply, so this will be rho g 2 pi r. So sorry, tau will also come, right? Just 1 second. So plus 2 pi r dx tau at r minus 2 pi r dx tau at r plus dr minus rho g 2 pi r dr dx sine theta is equal to 0. So this will be mu upon r d dr r du dr is equal to dp dx plus rho g sine theta. So boundary condition 1 will be at r is equal to 0, del u del r is equal to 0, and r is equal to capital R is equal to 0. So then this thing comes, the velocity, if you will solve it, you will find this expression. So average velocity, if we will find, this will be 0 to r u r 2 pi r dr upon pi r squared. So if you solve it, this will be del p minus rho g l sine theta d square by pi 32 mu l. So this will the average velocity, and the volumetric flow rate will be del p minus rho g l sine theta pi d square upon 128 mu l. So this is what we will use in this problem. So what is given? Density is given as 888 kg per meter cube. Viscosity is given as 0.800 kg per meter second. Delta P is given as 745 minus 97 is equal to 648 kilopascal. And cross section is given as pi d square by 4 is equal to pi 0.05 meter whole square by 4 is equal to 0.001963 meters. Now this we will use like for the first case, theta is equal to 0, sine theta is equal to 0 for case 1. So the volumetric fluid we need to find out. Like you take 2 minutes to solve this, then we'll proceed with the solution. I think proceed. Like we should proceed with the solution. So what will happen is that, so first case it is horizontal, that means theta 0, sine theta is 0. So for this, just 1 second please. So the volumetric flow rate horizontal is equal to del p pi d to the power 4 128 mu L. So if we'll put all the values, it will come about to be 0.00311 meter cube per second. For the second case, there is uphill flow with an inclination of 15 degree. That means theta is equal to plus 15 degree. So this will be uphill, volumetric fluid uphill will be delta P minus rho GL sine theta pi d to the power 4 by 128 mu L. So this will be 0.00267 meter cube per second. For the third case, there is a downhill flow with an inclination of 15 degree. That means theta is equal to minus 15 degree. So the volumetric flow rate downhill is equal to del P minus rho G L sine theta pi d to the power 4 by 128 mu L. So sine minus 15 degree will be there. So this will be 0.00354 meter cube per second. So this is what it is for this question. Now what they have asked, the flow rate is what is said, verify the flow is laminar. So we will take the maximum flow rate. So the maximum flow rate is for the downhill as expected because of the gravity. So average velocity in that case for downhill is v dot upon cross sectional area 0.00354 upon 0.001963. So this is 1.80 meter per second. So the Reynolds number will be rho v bar d by mu. So rho is 888, average velocity is 1.80 and dia is 0.05 meter, and this is viscosity is 0.800 kg per meter second. Everything is given, so this will come out to be 100, which is much less than 2300. So obviously if this is laminar, then others will be laminar as well. So the flow is laminar for all three cases. Okay, so let's proceed to the next question. Okay, so water at 60 degree Fahrenheit, density is given and viscosity is given, is flowing steadily in a 2-inch diameter horizontal pipe made of stainless steel. Make sure stainless steel is, you understand stainless steel, so epsilon is given in the chart that is given below. At a rate of 0.2 feet cube per second, the volumetric flow rate is given. Determine the pressure drop, the head loss, and the required pumping power input for the flow over 200 feet long section of the pipe. So the Colebrook equation is given. So you can either use Moody's chart or you can use Colebrook equation to find the friction factor from the Reynolds number and epsilon by d. So yeah, you solve this, you take 2 minutes to solve this, and then we'll proceed with the solution. So there are many more questions left. I don't think I'll be able to solve all of them, but yeah, I'll give you as homework. You can solve that, and answers also I'll tell you. And what I'll do is, along with this presentation, I'll also upload the solution for all of them. Right, so you can solve, like you can check the solution, and you can do it by your own. Okay, so about this problem, let's proceed. So density is given as 62.36 pound per feet cube. Excuse me. Viscosity is given as 7.536 10 to the power minus 4 pound per feet second. The flow rate, the pipe length, and the pipe diameter are known, so we can calculate the average velocity and the Reynolds number to determine the flow regime. So the average velocity is volumetric flow rate is given, so AC is equal to 0.2 feet cube per second pi into 2 upon 12 feet square upon 4. So this is come out to 9.17 feet per second. Reynolds number is equal to density velocity d by mu. So this will come out to be 126400. So this is double it, as it is far greater than 4000. Now epsilon by d is 0.00042. So from Moody's chart, f we got as 0.0174. So from and also from the Colebrook equation, if we'll put the values and we'll solve by using a solver, so we'll get as 0.0174. The pressure drop as delta P is equal to delta PL is equal to pressure loss in this case. So this is FL by D rho V square by 2. So it is 11.8 psi. It came out to be this. Now then the head loss is equal to delta PL by rho G. So FL by D V square by 2G. So what this came out to be? This came out to be 27.3 feet. The pumping power of the pump is equal to the volumetric fluid into pressure difference. So that is pressure difference means this one, right? So this is also 1700 pound force per feet. So this will come out to be zero point 0.2. This is 0.2 feet cube per second, and this is 1700 pound force per feet square. So this came out to be 461 watt. And multiplied this by 1 watt half 0.737 pound force feet second, pound force feet per second. Yeah. So let's proceed to the next question. So heated air at 1 atmospheric pressure and 35 degrees Celsius is to be transported in a 150-meter long circular plastic duct at a rate of 0.35 meter cube per second. If the head loss in the pipe is not to exceed 20 meter, determine the minimum diameter of the duct. So third Swami-Jain formula, like here three type of like here what is happening is that we need to guess put guess values. So if we put guess values, we can take iterative method, or friction factor we can also calculate by using that Coley equation, Colebrook equation, and also we can use to calculate the diameter, we can also use this Swami-Jain formula directly. So anything that you prefer. So we'll solve by all these methods. So let's proceed. So first of all, what is happening is that this question number 4. So average velocity we'll find out. This is 0.35, the volumetric flow rate, meter cube per second upon pi d square by 4. So pi d square by 4. So this is equation 1. Reynolds number is V bar d by nu. So this is V bar d by nu is 1.655 into 10 to the power minus 5 meter square per second. This equation 2. Now 1 upon root f is equal to minus 2.0 log 2.51 by Reynolds number root over f. So this is equation 3, and the fourth one is 20 is equal to f 150 meter by d v square by 2 9.81 meter per second square. So this is equation 4. No, then if we'll use the simultaneous solution of equation, so this 4 if we'll solve, we'll get d as 0.267 meter, f as 0.0180, and velocity, average velocity 6.24 meter per second, and Reynolds number as 100,800. Diameter can also be determined by using third Swami-Jain formula that is given here. So if you will use this, then diameter will get as 0.271 meter. Or iterative method also we can use for iterative method. So by iterative method, if you will solve, we'll find diameter to be 0.267. There is a related question to this. So now duct length is doubled while its diameter is maintained constant. If the total head loss is to remain constant, determine the drop in the flow rate to the duct. So previous diameter was this one. So now we will use iterative method in this problem. So we'll solve in detail. So what will happen is that HL is given as F L by D V square by 2G, right? So V bar we can get as 2G HL, okay, 2G HL upon FL upon D. So this is V bar. Now iteration 1. So let's guess the first value of F. So let us guess it as 0.04. So if this is it, then V bar will be root over 2 into 9.8120 upon 0.04 multiplied by 150 multiplied by 2 upon 0.267. So this will come out as 2.955 meter per second. Now the Reynolds number came out to be 4.724 into 10 to the power 4. So from Moody's chart we got as F corrected value is equal to 0.0212. Now the iteration 2. So for iteration 2, F is equal to 0.0212. Average velocity is came out to be 4.059. Reynolds number came out to be 6.489 into 10 to the power 4, and F corrected came out to be 0.01973. Now iteration 3, F came out to be 0.01973. The average velocity is 4.207. Reynolds number 6.727 into 10 to the power 4. F corrected is equal to 0.01957. So iteration 4 is F is equal to 0.01957, velocity is 4.224, Reynolds number is 6.754 in 10 to the power 4, F corrected is equal to 0.01956. And for the iteration 5, we can get, like, if we'll do this again, we'll get the same value of F. So this is the final value of F. Okay. Now let's proceed to the next question, that is, so it said that water at 10 degrees Celsius flows through a large reservoir to a small reservoir through a 5 centimeter diameter cast iron pipe system. So what we need to do, we need to determine the elevation Z1 for a flow rate of 6 liter per second. Epsilon is given. So to find that. So I'll give you 1 minute to 2 minutes rather to solve this. And then we'll proceed with the solution. Okay. So about the question number 6. So 89 meter of piping is there. Entrance the KL for the entrance is given as zero point 0.5, right? Yes. So for the standard two standard clenched elbows, so KL for that is given as zero point 0.3. So it is 2. And for the fully open gate valve, so KL is zero point 0.2, and the submerged exit KL is 1.06. So 1 and 2 are the free surfaces. So P1 and P2, like if we'll apply the Bernoulli equation at 1 and 2. So P1 and P2 both are at atmosphere. So this will get cancelled out. And Z1, velocity 1 and 2 will be 0. Both at 1 and 2. So we will find that Z1 is equal to Z2 plus HL. So HL is the total loss, that is major loss plus minor loss. So HL is equal to major loss means FL by D plus minor loss means summation of all KL V square by 2G. So the dia of the pipe, so we need to find the average velocity V upon AC. So that the pipe is constant, so there will be only one average velocity. So this pi D square by 4. So this is equal to 0.006 meter cube per second by 0.05 meter whole square by 4. This is equal to 3.06 meter per second. Reynolds number is rho V D by mu. So this is equal to 999.7 kg per meter cube. 3.06 meter per second and 0.05 meter. 1.307 into 10 to the power minus 3 kg per meter second. 11700. So if Reynolds number is very far greater than, so this Reynolds number is far greater than 4000, so the flow is turbulent obviously. So epsilon by D we have calculated as 0.0052. So by the Colebrook equation, we already know Colebrook equation, we can get F as 0.0315, and the summation of all KL is equal to 0.5 plus 2 multiplied by 0.3 plus zero point 0.2 plus 1.06. So this will be 2.36. So the total head loss is equal to F is 0.0315, 89 upon 0.05 plus 2.36 multiplied plus 2.36 multiplied by V square. V square means 3.06 whole square by 9.81 multiplied by 2. So this will come out to be 27.9 meter, right? So the elevation of the source also we need to find out. So this is Z2 plus HL, so this is 4 plus 27.9, 27.9. So this will come out to be 31.9 meter. The free surface of the reservoir may be 31.9 meter above the ground level to ensure the water flow between the two reservoirs at the specified rate. Yeah. So we have few more questions left, and those are very relatively easy questions. So I think we'll complete by today itself. So which of the following is the correct way of reducing the entry loss for a flow entering a sharp-edged pipe from a large reservoir? Obviously, a well-rounded inlet cause lesser the entry loss as fluid can flow the boundary layer without separation, right? So option B is correct. Next is this question, where a steady push in the piston in the figure flow below causes a flow rate of 0.15 centimeter cube per second through a needle. Through the needle, the fluid has density and viscosity is given. What is the force required to maintain the flow? So we need to select the closest integer. So I think it's very easy. So about this, the velocity of the exit from the needle is B1 is equal to Q upon A. So the velocity we need to find out. So 0.15 pi by 4 into 0.025 square, 25 square. So this will come out to be 3.06 meter per second. So this is the velocity at the exit from the nil. So if we apply the Bernoulli equation, P1 by rho g plus V1 square by 2g plus Z1 plus H for F1, that is one side, that is one pipe 1, and HF2 for pipe 2 is equal to P2 upon rho g plus V2 square upon 2g plus Z2. So Z1 and Z2 are equal, right? Z1 is equal to Z2, so this will get anyhow cancelled out. V2 is equal to 0, obviously. So this large tank, so large pipe, so V2 is equal to 0. HF1, HF1 is equal to 0. Friction loss, as it is too small, considered to be too small. So assume laminar flow, so the pressure difference in the piston is P1 minus P2 upon rho g is equal to HF1 plus V1 square by 2g. So if we will calculate all of them, this HF1 is 32 multiplied by 0.002 multiplied by 0.015 multiplied by 3.06 upon 9.00 multiplied by 9.81 multiplied by 0.00025 square plus this whole velocity is given as 3.06 square upon 2 into 9.81. So if we'll solve this, we get 5.79 meter. Now the force required for the flow. What is the force required for the flow? Is nothing but the pressure. Pressure we have already calculated, multiplied by the area of the piston. So the pressure and pressure multiplied, so this is P2 minus P1, that is the delta P upon rho g. So rho g we also need to multiply. So rho is 900, g is 9.81 multiplied by the pressure difference is 5.79, we have already calculated, multiplied by the area. So area is pi, that is 3.1415 multiplied by area is 0.01 square upon 4. So this we have solved to get 4 Newton of force, that is option. Yeah. So next question is, which of the following statement is true? Gradual expansion in pipe has smaller loss coefficient. Gradual expansion has larger loss coefficient because of flow separation. Obviously, because of flow separation take place due to the sudden expansion of the fluid leaving the contact at the walls, and the formation of the eddies near the wall of larger tube. So this is option B. For the flow of a liquid through a circular pipe of radius r0, the velocity profile is given. Find the kinetic energy correction factor for the. So this we already know that this option, the question number 10, right? So the average velocity first we need to calculate. So this is 0 to r0 v 2 pi r dr upon pi r0 square. So this is 0 to r0, 6, 1 minus small r upon r0 whole square, 2 pi r dr. So this is pi r0 square. So this is equal to, this came out to be 1 unit. Now the kinetic energy correction factor is equal to 0 to r0 v cube by, sorry, multiplied by 2 pi r dr. So this is v bar cube pi r0 square. So this is v cube, not v bar cube. So the velocity profile is already given. So 0 to r0, 6, 1 minus small r upon r0 whole square whole cube 2 pi r dr upon v bar cube pi r0 square. So if we will solve this, we'll get 54 upon 7, that is option B. Okay, so let us proceed to the next question. I hope you are understanding what I'm explaining. So I'll also upload the solution manual so you can get an idea of like what is happening. So it is freshly written. So for the case of flow through branch pipes, that is series or parallel, which of the following does not hold true? So we already know that there can be only one value of head at a given point. in case of flow through branch pipes. So the last one is not. Okay, next question. The transfer of energy by viscous dissipation is depend upon the viscosity, thermal conductivity, the steam velocity and steam temperature. Group these quantities into dimensionless Brinkman number. Which of the following is proportional to mu? So what do you think about that? Like m is m L to the power minus 3 to the power minus 1, right? K is, so this is mu. So this K is m L to the power minus 3 to the power minus 1, right? The U is equal to the steam velocity. Stream velocity is L to the power minus 1, and T naught, that is temperature, is theta. So we can form only one dimensionless group with these quantities. That is pi is equal to K to the power A, U to the power B, T naught to the power C, and U. So pi dimension is equal to m L T to the power minus 3, T to the power theta to the power minus 1, A, L T to the power minus 1, B. Theta to the power C, m L to the power minus 1, T to the power minus 1. So m will take together m A plus 1, L A plus B minus 1, T minus 3A minus B minus 1, theta minus A plus C. Therefore, A plus 1 is equal to 0, A plus 1 minus, A plus B minus 1 is equal to 0, minus 3A minus B minus 1 is equal to 0, and minus A plus C is equal to 0. So if we'll solve this, we'll get A is equal to minus 1, B is equal to 2, and C is equal to minus 1. So Birkman number is mu U square by KT naught. So yeah, now we'll solve one problem on dimensional analysis. So a prototype ship is 35 meter long and designed to cruise at 11 meter per second. Its drag to be simulated by 1 meter long model pulled in a tow tank. For Faraday scaling, find the tow speed. See, it's just a scaling parameter. So you know the Faraday scaling parameter, so how to use that for the model and the prototype? Just use that simply. Okay, so for the Faraday scaling, Vm upon root over Im is equal to Vp upon root over I, or Vm is equal to 11 multiplied by root over 1 by 35. Right? Yeah. So this is equal to 1.859. That is options. For the next problem is related to this problem. So for this, determine the ratio of the prototype to model drag. This is pretty simple. So model to prototype, that is Vm upon Vp whole square, Lm upon Lp whole square. L or I, whatever we have defined, anything. So this is root over 1 upon 35 whole square, 1 upon 35 whole square, 1 upon 42900. There's option. So the last question for this session and for this course as well. A prototype spillway has a characteristic velocity. Velocity is given. Characteristic length is given. A small model is constructed using Froude scaling. What is the minimum scale ratio of the model that will ensure the minimum Weber number is 100? Both flows, the water temperature is 20 degrees Celsius and density and surface tension is given. So for this, first of all, Weber number for the prototype is Weber number for prototype is density, velocity square, length and surface tension. So this is 998 multiplied by 3 square multiplied by 10.073. So this is equal to 1.23 into 10 to the power 6. Now for Froude scaling, Weber number for model upon Weber number for prototype is density of model, density of prototype upon velocity of model, velocity of prototype whole square, length of model, length of prototype, surface tension of prototype, surface tension of model. So this is 1 root sigma square, sorry, root 6 square 6 upon multiplied by 1. So this is okay. So if we'll solve this, this is alpha square. So this is 100 upon 1.23 multiplied by 10 to the power 6. So this is alpha. So alpha will be just root of this. So this will come out to 0.009. Thus the model Weber number will be greater than 100, and alpha should also be like, that is Lm upon Lp should also be greater than 0.009. That means 1 upon 1. So this is option. So this is the solution for this. Yeah. So that's it for this session, and that's it for this course. I hope you have enjoyed the session, the problem solving session, all the problems you have understood. And for today's session, I'll upload the solution manual along with the question presentation, the presentation that includes all the question. I'll upload both of them in the folder, and the folder link will be shared to you. And I hope you have enjoyed all the session and you have understood, or your doubts are being clarified over here. So yeah, keep enjoying and keep studying, and keep clearing your concepts about this, because fluid mechanics is very important course that will be used for you, like it will be applicable in multi dimensions, like in multi pal applications, right? In real life applications, in many places you will get the application of fluid mechanics. So yeah, it was very enjoyable for carrying out these sessions. So bye bye for today, and for this course, maybe I'll conduct some other sessions and other courses. So meet you guys on the next semester.